This is the presentation on rivers and flooding, which is the first module of the course on water management. I am Nathan Bowden, your instructor for this course. In this first module, you will learn what watersheds are and the role that they play in the natural history of rivers, how scientists describe and measure rivers, including their discharge, flow, base level, and longitudinal profile, how rivers erode, carry, and deposit sediment, what causes floods, and how they develop floodplains, as well as how people measure and forecast floods, and how people attempt to control or mitigate flooding. Floods can be a very destructive part of the water system. An example of this was a flood in the Mississippi River in 1993, which submerged many towns, including the city of Valmeyer and nearby Kaskaskia, where water reached the depth of 6.5 meters in the floodplain community. This community decided later that year to move the entire community to a higher location so that would be out of the flood's path. A few basic river concepts that you will need to learn are what watersheds are, how to calculate flow, discharge, and the impacts they have on channel shape, what base level is, what a longitudinal profile and gradient of a river is, what the effects of erosion, sediment transport, and deposition are, what floodplains are. Watersheds are the area of land around a river system which contribute to the catchment of the river. That is to say, as you see here on the right-hand side, all of the land surrounding any of the tributaries of a river which eventually flow into that river. Watersheds, come in many different sizes, and one of the world's largest watersheds in South America is the Amazon River watershed, which comprises approximately 40% of South America, and which is anywhere between 6,300 and 6,800 kilometers long, and is 1/5 of all fresh water entering into the world's oceans, and that is all the world's oceans. Flow, discharge, and channels. Discharge is calculated as the cubic meters per second, which is, that is to say, area or cross-section times the velocity of a river. Discharge is the volume of water that passes through a defined point per time, in most cases seconds. Discharge is calculated by multiplying the cross-sectional area in square meters of a stream channel by its flow velocity meters per second. And as you see here on the left-hand side, the cross-section of three different rivers, while the rivers have a different cross-section, can be the same size. So in the case of these three rivers, they all have the same cross-section. Discharge of a river depends mainly on two factors: the watershed size, that's the amount of land which contributes to the river, and the amount of precipitation that falls onto that land. If discharge is too great for the channel to carry it, it is overtopped, it overflows the levees, and this is called a flood. Base level is the elevation at which a river can no longer flow or erode deeper into the ground. For many of the world's largest rivers, this is sea level, but not necessarily. Longitudinal profile is the channel, which is a graph at which the elevation of the river throughout its distance is charted. Erosion occurs as the downcutting along the gradients, which are very steep. This would be, that is to say, erosion is very high in gradients that are steep, which is shown here on site 1, going through the mountains. And gradient is low as the river approaches the base level. At this time, the river will meander more, which is to say it will longitudinally go left and right, and they will also quite often broaden. Erosion is quite fast in fast-moving streams. So in a headwater, which is the beginning of a river, they are quite commonly fast, and they cut steeply into the channels. The Arizona's Grand Canyon is an example of how effective erosion can be. In this case, you see the Colorado River cutting into the Colorado Plateau. Rivers can also erode sideways, and in this form they form cutbacks along the riverbanks. Rivers, this especially happens when the gradient is lower. On the outside of this bend is where the cutback occurs, and that's where the lateral erosion happens. And on the inside of the river, you have a bank, which is called a point bar. And this is where the deposition of the erosion occurs. As you continue further along the river and it approaches its base level, broad loops and curves can form. These bends, which are also called meanders, change throughout deposition. These bends can sometimes form into oxbow lakes, which are meanders that cut through themselves. And at certain points of time, these meanders are cut off, and a lake forms. These are called oxbow lakes. Sediment within a river, there are approximately 3 different types. The first one is bed load, which is the larger and heavier rocks within a river. These are dragged, rolled, or skipped along the river bottom, and that's just called saltation. Finer particles, which are suspended in the water, in the river itself, is called suspended load. And dissolved minerals and organic materials, which are leached from the soil or the rock within the watershed. And these are called the dissolved load. The dissolved load is a very important part of a river and of flooding, because these dissolved minerals enrich the soil around the river. A stream carrying capacity is at a specific velocity and discharge, the maximum amount of bed and suspended load it can carry, and this is the carrying capacity. The capacity is high when velocity and discharge are high. Therefore, more erosion occurs at this time. Material transported in large rivers consists mainly of suspended load and not large rocks or dissolved load. An example of one of the world's richest rivers in suspended load is the Yellow River in China. This river has up to 70% of its volume being suspended load. Channels are also very rich in sediment deposits. When a river loses its ability, so the opposite side when it's eroding at a high velocity, when it loses its ability to transport sediment, mostly due to decreasing velocity, this is when sedimentation occurs. In rivers with abundant sediment, that means they have a lot of sediment, a lower velocity zones within the river's channel go into depositional areas. And these are often braided through each other, as you see on the picture on the left-hand side. These often are fan-shaped bases, and on the left picture you see an alluvial fan, which is when deposit is reaching a local base level. It may enter a valley, or on the right-hand side you see the Mississippi River Delta, when the Mississippi River is depositing its sediment. The discharge of Mississippi Delta is a very complex history and has evolved through time. But this time, the delta, which is the discharge area of the Mississippi River, comprises of approximately 40,000 square kilometers. The older sediment lobes being just a section, have compacted and are now underneath newer areas. And on the right-hand side, you see the historical pattern of the different sedimentation areas and lobes. A floodplain is typically a lower level or a very horizontal level to the bank of the river, and this is the area of land next to a river which is typically flooded at a certain time when the river can no longer fit into its channel. Many people live on the banks of the rivers in the floodplains throughout the world. In fact, most of the world's largest cities are built on a floodplain on the banks of a river. There are perils of living next to floods. Floods are occurring when the discharge of the river is so great that it goes over its natural or artificial banks. And the word that we use for an artificial bank of a river is called a levee, the plural being levees. Ancient Egyptian civilizations relied on this natural flooding, as I mentioned before. When it floods, the deposition of the nutrient-rich silt goes into the floodplain to enrich the soil for their agriculture. Unfortunately, to control the floods, they built rivers, dams on the rivers, and this, while it did keep from excessive flooding, it also kept the reestablishment of nutrients at lower than natural levels. When a river overtops its banks or its levee, this is what we call the flood stage. The flood crest is the highest level above flood stage the river reaches during a flood. Floods can form quickly or slowly. In the top example here, there was a very large thunderstorm that occurred, and the Rapid Creek, the name of the creek was Rapid Creek. It overflowed after intense rain, and this devastated the city of Rapid City in South Dakota, killing 238 people. And the opposite side of that is raining that occurs over days time. This is typically light rains, but since they occur over such a large amount of time and the watershed is so large, this can quite often be just as devastating, if not more devastating, in this example of the Mississippi River. So intensity and duration and timing of precipitation are important factors to consider in flood severity. These severities can also be seasonal. In the case of the Pineapple Express, it's a rainy season of the northwest of the United States and the western part of Canada. In this case, the warm, moist air coming from the South Pacific, such as Hawaii, this warm air is going north comes into contact with the mountains and then rains in the Sierra Nevada mountains. This often occurs along with the melting of the snow, and these two things combined lead to heavy flooding in the U.S. Pacific coast and in Canada. But seasonal raining seasons are quite common throughout the world. Failing dams and flooding. Dams can be formed naturally or engineered. These can be formed through landslides. An ice dam, which we'll see shortly. Also a constructed dam, of which there are more than 75 dams within the United States alone. And dams have far-reaching effects on drainages and can have catastrophic effects if they fail. Here is an example of a lake which was formed behind an ice block, an ice dam of 1,250 meters height. It blocked the Clark Fork River Valley in western Montana, making a lake that was 320 kilometers long and held over 2,000 kilometers of water. The volume of the water which flowed through the rivers when this dam failed, this naturally forming ice dam, was so much that it was 10 times the flow of all the rivers in the world at this time, and it went through the land of the Columbia River, scouring the land and producing the channeled scablands as they're known today. Farming practices can have a negative impact also on flooding, because there's no longer a topsoil on the land, and the land itself is bare. More water, precipitation, floods into the rivers, which increases the suspended load and also degrading the water quality. Wetlands, on the other hand, are a natural occurring mechanism which can control floods, and which these form mostly on floodplains, and they hold on to the water as well as filtering out pollutants and suspended solids. To combat this degradation of water quality, many dams are going through some controlled flooding, which they allow the sediment to go through the dam at controlled intervals. And so here you see before the flood, where the sediment was quite low, and the sandbars also quite low. After the flood, the sandbars reformed, and the nutrients were allowed to go back into the soil. Flash floods are a type of flood which forms extremely rapidly. An example of this is within a 3-hour period. The Big Thompson River rose from 3.9 cubic meters per second. It had a discharge of 3.9 cubic meters per second. In that 3 hours time, it rose to 884 cubic meters per second. This formed a 6-meter wall, 6-meter high wall of water, which went through the Big Thompson River basin, destroying everything, including a highway, and killing 145 people. Riverine floods, or riverine floods, depending on how you want to say it. Riverine floods are typically slower forming floods. They are regionally forming. They typically do have even more volume of water. However, and why they have more water is that they come from several different tributaries or smaller rivers that feed the larger river. But while it is slower forming, it can quite often be more devastating because of the time it takes. These riverine floods typically go over several days. They result from multiple rainstorms and spring runoff events from melting snow. A typical example of these large forming rain events that produce very large and slowly building floods is in the American Northwest, where a confluence of warm, moist air from the Gulf of Mexico meets a descending cool, dry air from Canada. These form over a very large landmass, and they form several tributaries which feed into the Mississippi and created, in 1993, a very large flood. We can use several different tools in understanding floods. The first is a hydrograph, the flood recurrence interval, the 100-year flood, flood probability, and also some using historical data in order to look at future probability of flooding. A stream hydrograph is quite simply the recording of the discharge of a river over a year. And here what you see here is the hydrograph of the South Boulder Creek in Colorado over 1 year. To determine a 100-year flood, you will have to record how often the river reaches its peak every year and plot that discharge by year. And this is called a flood frequency curve, which is a plot of annual flood discharge and the reoccurrence intervals. Rivers with many years of annual flood records show a systematic relationship between peak discharge and recurrence interval. The relationship enables a peak discharge of a flood having a recurrence interval of 100 years to be estimated. And a 100-year flood's estimated size is a benchmark for evaluating a river's flooding capability. And this 100-year flood is very often used in risk analyses when building infrastructure. If you want to build, say, a highway or a bridge, you want to build it so that a flood that may only happen once every 100 years would not devastate the river, the bridge, or the highway. A rating curve here is the relationship between a river's discharge and the corresponding stage for a particular period of time. Flood probability is the inverse of the recurrence interval. So that means if a flood happens in 100 years one time, it has only a 1% probability of occurring in any year. So that if you build a bridge which is at the 100-year flood level, there is a 99% chance that the river will not reach that bridge or highway in any given year. The 1-year flood is the inverse. The chance of that happening in a year is 100%. Living with floods. There are pros and cons to flood-controlled engineering in the case of levees and flood walls, which prevent the water from spilling over. Quite often, rather than over-engineering higher levees, so making sure the river will never overflow its levees or flood wall, they are purposely allowed to flood. In this case, it will re-sustain and add nutrients to the soil resources, which again contribute to also good for the soil and the farming, but also for biodiversity. Hazards in the United States are significant. The flood hazards are quite significant. In the United States, 104 people on average are killed each year, and this causes up to $6 billion in damage. In the 20th century, 12 floods killed 18,000 people or more, of which 10 were in China. and the death tolls have reached into the millions. Beside property damage and fatalities, other hazards that impact human health are caused by sewage, carcasses, drowned livestock, and pollutants such as paint, pesticides, and petroleum. And in the case of floods, quite often, you find everywhere there is water, the water that's drinkable, which is potable, it can be sometimes very difficult to find. How to mitigate this? You can alter the channel of the river, such as in the case of Los Angeles and the Los Angeles River. You can install flood control dams, such as the Three Gorges Dam on the Yangtze River, the world's largest dam, which produces also a very large amount of hydroelectric power. You can also divert the channel, or including floodways, and detention ponds to hold the river. A few examples of this is in the Bird's Point near Cairo, Illinois, where there's a very large floodway, which is an area of land. This one is 520 square kilometers, and that when the river floods, it will go into this land and hold the water. And this also is it's quite common. Another example is the Natchez and Baton Rouge, the Old River Control Complex. In summary, rivers play a key role in water and rock cycles. They transfer water and sediment. Watersheds are where water collects and flows together to form streams and rivers. All Earth's spheres interact in watersheds. Amount of water flowing in a river, its discharge, is related to its channel, cross-sectional area, and flow velocity. A river's character changes as a function of natural influxes of water and sediment, or from people's effects on its watershed. Rivers flow and carry sediment to their base level. Local base levels are defined by places like lakes. Ultimate base level is sea level. Steeper river gradients have higher velocity flows. Rivers can erode their banks and channels, and sediment is transported as bed load, suspended load, or dissolved load. Most sediment is deposited where rivers near or reach their base level. Rivers develop floodplains. Earth systems interact on floodplains. Floods irrigate wetlands, replenish soils, and help create habitat. Flash floods commonly develop after heavy precipitation. Riverine floods have more widespread sources and take longer to develop than flash floods. Extrapolation of historical annual flood discharge and recurrence intervals enables size of an annual flood having a recurrence interval of 100 years to be estimated. Structural and non-structural controls are used to manage rivers. Although there are many benefits, floods causes more damage than any other natural disaster.